Okay, so let's talk about carboxylic acids. And a generalized structure of all carboxylic acids, they look like this. Notice that this carbonyl carbon is sp2 hybridized, so it's going to be 33% S character in trigonal planar, if I can get my colors here. This oxygen here is going to be partially negative. That carbon there is going to be partially positive. This oxygen will be partially negative, and this hydrogen will be partially positive. And so that's something that's going to play a role in reactivity later on whenever we're talking about this. But before we can start talking about the reactions and the properties of it, let's talk about the nomenclature. So for any type of, substituent group, there's two types of nomenclature. There's when it's involved in a chain, an alkene or an alkane chain, and whenever it's a part of a ring. So when it's a part of a chain, there's two steps that you want to do. The first step is just to simply number the longest chain. The second step you want to do is to give it the number one priority, your carboxylic acid. And then the third step that you're going to do is just going to rename it. You're going to remove the E, add to that the suffix of oic acid. So that's how you would do that. Now let's talk about how you would number a ring system. And I'm going to switch colors so that I don't get mixed up. So whenever you have something that's a part of a ring, you simply just name it as a substituent, but end it with, well, here, I'll just write out my steps first. So you name as your number one, name it as your number one substituent. What are you naming as your number one substituent? You're naming your carboxylic acid. Whoa. As a number one substituent, a part of your rings. So now let's talk about the physical properties of carboxylic acids. So they obviously can exhibit dipole-dipole interactions. I feel like that should be dipole. Don't know why that got left off. But I feel like I kind of already addressed that in the initial part of the video. But let's just review. So over here, the oxygen partially negative, the carbon is partially positive. This oxygen here will be partially negative, and this hydrogen here will be partially positive. So I hope that you can see just by seeing that OH group there that this totally has the potential for hydrogen bonding. So let's just say I have another carboxylic acid adjacent to that, and I'll say there's my R group. It doesn't really matter where I position these things. And there's an OH group. Well, because it's a hydrogen bonding, I'm going to go ahead and change the colors here to make sure that I'm drawing that in green. That's a partially negative, that's a partially positive molecule there. You can totally have hydrogen bonding taking place within that molecule. Hydrogen bonding contributes to the formation of dimers, and that's I guess in terms of a biological molecule, that's really important. And they are super, super polar, which means that they're very easily create these net dipole interactions are much stronger than usual. So now I'm going to talk about the types of solubilities. So I hope you remember that any time you have 5 carbons, or greater than or lesser than, depending on what you're talking about, and a polar functional group, but in this context a carboxylic acid, anytime you see this, depending on what else can be said about that. So if you have, for example, less than or equal to 5 carbons, or say that you have greater than 5 carbons in your molecule. If you have greater than 5 carbon in your molecule, it's going to be water insoluble, but it will be fat soluble. And this is where I thought this was interesting. This is where the phrase fatty acids come from. If you ever get involved in nutrition or want to know about how people can scam you out of your nutritional supplements, that's how you do that. So anything that has less than 5 carbons in it will be water soluble and obviously fat insoluble. Cool. Okay, so with spectroscopy, there's really not much that can be said about this other than the fact that they give, for obvious reasons, your carboxylic acid groups are going to give very unique spectroscopy. So for infrared, and I should have done this in red, there are 2, I guess, types of structures that are going to give unique sequences. The carbonyl carbon and then the OH group. And I promise you, spectroscopy is super important. I don't know why. They just love to ask questions about that. But it's going to give around 1710 inverse centimeters And for the hydroxyl group, you're going to get readings at anywhere about 25,000 to 35,000 inverse centimeters. Now, for proton NMR spectroscopy, what you will see, that should be a different color. What you'll see, well, obviously for proton NMR and then for carbon-13 NMR, you're going to see two, I guess, kind of unique things. For proton NMR, it tends to have readings anywhere from about 10 to 12 parts per million, and that's mostly because of the hydroxyl group. And then around carbon-13 NMR, because of the carbonyl group, you're going to see absorption readings at about 170 to 210 parts per million. Cool. So now let's talk about things that are by far more important. How we can create carboxylic acids, or how we can prepare them, as it's just a slang term of making something. So the first way that we can do is by oxidation of primary alcohols, and this is review for most of it. So say I have a primary alcohol, and I treat that primary alcohol with CrO3, and it could be any of those groups when we talked about, I think it was chapter 16? I'm not sure. Anyways, and you treat that in H2SO4 and water, and whenever you do this, the outcome of that is going to be a carboxylic acid from that. But you can't use the other reagents that you're talking about. Well, I mean, you can use the chromate, you can use, I think, sodium and potassium derivatives of this. Anything that you put in a solution that can give you chromic acid will be used for this. Now, let's talk about oxidation of benzene, of alkyl benzene. So now let's talk about oxidation of alkyl benzenes. And they kind of have a generalized structure like this, or generalized mechanism like this, where I'm just going to use a methyl group as an example, but just know that it could work with any alkyl group. So say you have a methyl group there, and I run this reaction with potassium permanganate. Hope you can see that. And what you get out of that is a carboxylic acid. This pen is really hard to draw with. I'm just going to go ahead and redraw over up here that my reagent for that reaction is potassium permanganate. Cool. And then the other type of way that we can make this is by ozolysis, or ozone hydrolysis, as some people call it. And there's two, I guess, types of things. So remember that when we're talking about this, you're talking about alkanes, or alkynes. Sorry, I should watch my nomenclature. And there's terminal alkynes. This should all be review. And then internal alkynes. Terminal alkynes have a generic structure like this, whereas terminal have a structure that involves the use of a hydrogen. I should really watch the way that I'm drawing things. And then the other one has another R group there. So when you treat either one of these reactions, though, with the product of O3, ozone, in water, you get cleavage, essentially, of that triple bond. The mechanism behind it's kind of complicated. But anytime you have a terminal, what you end up with is a carbon dioxide and a carboxylic acid, which is what we're trying to make here, or what we're interested in making. And for this, for an internal, both of these have R groups on either side, so you get two carboxylic acids times 2. Cool. So carboxylic acids can, obviously being acids, can take place in acid-base reactions, predominantly Bronsted-Lowry acid-base reactions. So I'm just going to go ahead and label that over here. That's say Bronsted-Lowry reactions. So I'm going to go ahead and just redraw my structures of a carboxylic acid here. So the basic, or the acidic, portion of this molecule resides in anywhere between here. This whole area is called, this is the acidic. I think we take an entire chapter on the acidity of the OH bonds. And so you go ahead and just react this with generic, I'll just put it in blue, some type of a generic base. We don't care about the type. And what you obviously are going to get is a carboxylate anion. That oxygen will have a negative formal charge. And so what can we say about this? Well, what I can say about this is that this is a very, whenever we remember when we talked about acid-base reactions in organic chemistry, this is a very stable conjugate base. And so if you have a really stable conjugate base, well, there's consequences of that. If you have a stable conjugate base, then that means that your acid is strong. The more stable it is, the more stronger it is. Why is this a stable conjugate base? Because of two reasons, and I'm going to go ahead and define them, even though I think that this should be review, because it can be resonance stabilized. That's, in my opinion, the most important thing. And then secondary to that is the fact that it has the induction. What is the inductive effect determining with? Well, the oxygens being electronegative. Very good for induction there. Okay, so all carboxylic acids on average have a pKa value of approximately, those should be approximation signs, 5. So that's pretty, it's a strong acid, at least compared for an organic acid. That's incredibly strong. So in order for a base to be able to deprotonate this, remember that all reaction in chemistry are proceeding towards a more stable equilibrium. That should be an I, deprotonation. For a base to steal a proton from that, then the conjugate acid has to have a higher pKa value. So the conjugate acid for this, in order to deprotonate this, has to have a higher than pKa value because that's going to push equilibrium in the forward direction. All right, so substituted benzoic acids. So when you have electron donor groups, these tend to be destabilizing. The conjugate base, which is, remember, that the strength of your acid is determined based on the stability of your conjugate base. So if you're destabilizing your conjugate base, you're weakening your acid. If you have W, which is the generic term for electron withdrawing groups, that's going to stabilize conjugate bases, which makes your substance more acidic. Now, let's go ahead and I'm going to define each and every one of these terms with an example. So an electron donor group, if you remember whenever we were talking about electrophilic aromatic substitution, these tend to be EAS activators. And I have a whole video on what each and every one of those things is. For W, for the electron withdrawing groups, these tend to be EAS, electrophilic aromatic substitution reaction, deactivators. Cool. Let's talk about the generalized structure of an amino acid, which, I mean, I did, but what's unique about it is that there's both basic properties and then acidic properties. And I'm going to try to color coordinate these. So there's an acidic end to it. I think you can imagine what that is. And then there's a basic end to it. I think you can also imagine what that is. So I'm just going to go ahead and redraw that generalized structure. There's a hydrogen there. There's two compounds on either end there. And there's my R group. So the acidic end, as you may have probably guessed, is the carboxylic acid. And I'm really running out of room, so I'm going to draw this super tiny, but I think you can still see it. The basic end of it is the amino group, the amine group, sorry. Why? Because there's actually a lone pair on that nitrogen molecule. And this is a really good Lewis, it makes it a very good Lewis base. Now, let's say that we put this under some type of reactions, and we can, depending on the pH of this, because it has both acidic and basic properties, the solution pH totally can determine the conformation that it's in. So let's just talk about the solution pHs. There's neutral, or at least slightly neutral, approximately neutral. The other solution pH that we can have would be an acidic pH. And then the last one would be a basic pH, an alkalotic pH. Okay, so let's talk about each and every one of these. So when we're talking about an acidic pH in this context, I'm talking about a pH that is less than or equal to 2, which is kind of crazy. And at this pH, the overall molecule has a positive net charge. Net charge. So what would the structure of this molecule be? Well, you have your central carbon there. There's that. Carboxylic acid doesn't change. You can't make that a water group. But we now have NH3 with a positive charge, and then that's our R group. Cool. So when we're talking about it, whenever I mention that it has a neutral acidity, that really is approximation because the pH of it is about 6, which is not neutral. It's more acidic than it is the traditional conformation, which is kind of odd to me that most our body is actually more alkalotic than it is neutral form. But whenever you have a pH of 6, it is something called a zwitteron. Is the name of the conformation. So a zwitteron. And what this is it's like it has a net charge of nothing, but the carboxylic acid end is protonated. So I guess to draw out what this looks like, you have C, there's your H, there's your C. Oh, it's not a carboxylic acid now, we have a carboxylate group there. And NH3 plus, hope you can see that, and then there's the R. So all that's happened, the only thing that's different is as we've gone from a highly acidic pH to becoming more alkalotic, well, the first thing to go is the more acidic substance. So it's going to be deprotonated in that process. So I'm going to just draw out what a basic reaction would be. I think you can see the trend here. So as obviously the basic molecule being something that has extremely basic conditions, a pH of greater than or equal to 10, something crazy like that. So if the acid gave us a positive net charge, then as you may have guessed, the base gives us a negative net charge. And so what the overall structure of the molecule is, which is kind of crazy when you think about it, that both your base and your acid have been deprotonated in this structure. So let's go ahead and I'm going to draw it down here to give myself more room. So you have your carbon, there's your hydrogen, carboxylate, that's going to be back, negative formal charge, nitrogen, H2, and then your R group. So this has a negative formal charge, this has a neutral formal charge, and this has a positive formal charge. Acidic conditions, neutral-ish conditions, and then basic conditions. So, cool. The last thing that I really wanted to talk about is something called an isoelectric point. And this is a point in the pH where the amino acid exists primarily in the neutral charge. Generate that as PI, or isoelectric point. And this is the average value of both, this is also for, I should make a mention that this is for amino acid, but this is the average value of both the carboxylic acid end and the NH3 plus end, pKa values. So if you wanted to calculate this, you type in pKa of carboxylic acid plus the pKa of NH3 and then divide that by 2, and that would give you the isoelectric point. And I don't think I clarified because I feel like it was kind of implied, but this is for amino acids. Cool.